Hello and welcome to our introductory course on subatomic physics brought to you by University of Geneva. During this first module, we will give an overview of the objects that are treated by particle physics, namely matter, forces, and spacetime. We will also discuss how one goes about to characterize the strength of a reaction between particles with the concept of the cross-section, which is the central issue of our subject. At the end of the module, we will visit the laboratory of the nuclear physics course at University of Geneva to see a small example of how all of this works in practice. In this first video, we will take a quick tour of the elements of matter at the subatomic level. After having watched this video, you should know quarks and leptons by name and a few of their fundamental properties. You should be able to assign these constituents to families and to generations, and you should know the quantum numbers which are conserved in interactions among these particles. We are interested in this course in the subatomic structure of matter. Here's a schematic picture of the components of an atom. Of course, it is not to scale, otherwise the nucleus would be completely invisible. The atom consists of a positively charged nucleus of small size, of the order of 10 to the minus 14 meters, and a surrounding electron cloud, which is about 10,000 times larger, that is to say 10 to the minus 10 meters in radius, and negatively charged. For all we know, the electron is an elementary particle. Without internal structure and probably without size, it belongs to the family of leptons. Electrons and the nucleus are bound together by the electromagnetic force. The nucleus, on the other hand, is not elementary. It contains protons and neutrons bound together by the nuclear force. We will talk about the physics of the atomic nucleus in the next module. Protons and neutrons are not elementary either. They contain quarks bound together by the strong force. As far as we can tell today, quarks are equally elementary in the same sense as electrons are. But be careful. All of this describes just 5% of the universe. The rest is dark matter and dark energy, and we will introduce you to these two forms of matter and energy in module number 8. One can assign quarks and leptons to families according to their properties and to generations according to their mass, as shown in this table. The lepton families are shown on the left. All charged leptons have similar properties as the electron, which is the most well-known member of this family. The electric charge is -1 elementary charge. The neutral leptons, the neutrinos, are produced in radioactive decays. They have 0 electric charge and a very small mass. The quark families are shown on the right of this table. These are the constituents of proton and neutron, and of all particles which we call hadrons. There are also two types. The up-type quarks have an electric charge of 2/3 of the elementary charge. The down-type quarks have a charge of -1/3 e. Every family has 3 generations, almost identical copies of the first one, but a lot heavier than the first one. In the first generation, we find the familiar electron, the light neutrino nu L, the quarks up and down U and D. These are the constituents of the ordinary matter around us today. The second generation has the muon mu, the medium mass neutrino nu M, the charm quark and the strange quark, C and S. And finally, in the third generation, we find the tau lepton, the heavy neutrino nu H, the top and bottom quarks T and B. There is a quantum number which is called flavor, which distinguishes between the generations inside each family. It is conserved by all interactions except the weak interactions. The range of masses in this table is very, very large. Neutrinos are the lightest matter particles. Their masses are found experimentally to be below 2 electron volts, but they are probably rather in the range of milli-electron volts. We will talk about them in module 6, which covers weak interactions. The top quark has a mass as large as a hafnium nucleus. The hafnium nucleus has an atomic number 178 and a 72 positive electric charge. But as far as we know, the top quark is a point-like particle like all the others in this table. With these constituents, we can implement an order scheme, a descriptive nomenclature a la Linné. We call hadrons all particles which contain quarks. They are sensitive to stronger nuclear interactions, leptons are not. Baryons are bound states formed by 3 quarks. Mesons contain a quark and an antiquark, and the two together form what we call hadrons. The nucleons P and N are the lightest baryons. They form the atomic nuclei we find around us. And particles like the pion are the lightest mesons formed by quarks and antiquarks. There are no hadrons including a top quark because of its short lifetime. This quark decays before it can ever form a bound state with any others. Leptons, in the right of this table, are elementary in the sense that they are not composed of other particles for all we know. Observations are compatible with them having no size. They are thus point-like, and so are the quarks, but not the hadrons. We will often see the neutrinos nu-e, nu-mu, and nu-tau in tables of this sort. I don't adhere to this. These particles, nu-e, nu-mu, and nu-tau, are mixtures of the true particles with a specific mass, which we denote by nu-L, nu-m, and nu-h in this course. We thus respect their mass hierarchy and assign them to their respective generations according to that property, like we do for all other particles. The enormous strength of the strong force binds together quarks to form very stable bound states. To be sensitive to the strong force, particles need to have the necessary charge, which is called color charge. Quarks do have color charge, leptons do not. This leads to a whole zoology of hadrons as shown in this summary table. The particle data group is responsible to collect all the data concerning their properties. An exhaustive list of states, as well as a summary of their known properties, is available on the site of the particle data group, quoted in red on the bottom of this slide. On the left, you see a list of baryons containing 3 quarks, like the proton, which is a UUD bound state, and the neutron, which is a UDD bound state. On the right is a list of mesons formed by quark-antiquark pairs, like the positive pion, which is a UD bar bound state. Leptons are not sensitive to the strong force because they do not carry the necessary color charge. They thus interact only via the electromagnetic and weak forces and do not form long-lasting bound states among themselves. Here is a table summarizing some important properties of elementary particles. In the upper half of the table, you find the constituents of matter. Leptons and quarks are fermions of spin 1/2, as you can see. In the lower half, you find particles that transmit forces. These are bosons of integer spin. The charges are indicated in units of an elementary charge for each one of them, like the one of the electron in the case of the electric charge. Here we say that its charge is -1, which means that it's -1 times the elementary charge, E. The weak charge is called weak isospin, and it has 2 components in contrast to the electromagnetic charge, which has only 1 component. We denote them by T and T3, the total length of the weak isospin and its 3rd component. This charge depends on the orientation of the spin of the particle with respect to its direction of motion, which means it belongs on the helicity of the particle. The strong charge has 3 components. It's called color, and we use the abbreviation R for red, G for green, and B for blue to denote them. Color is a property of quarks and of gluons, which where the latter even carry a color and an anticolor simultaneously. For every particle, there's an antiparticle, which has the same mass, but all charge is opposite as indicated in this red table. Charges are additive quantum numbers. For a system of particles, the total charge is the sum of the charges of its constituents. But there are other quantum numbers that are conserved. The first one quoted here is the total number of baryons, i.e. the number of baryons minus the number of antibaryons in a system. This number is conserved. This applies in particular to quarks which have a baryon number of 1/3, and antiquarks which have a baryon number of -1/3. The total lepton number, i.e. the number of leptons minus the number of antileptons, is also constant in a closed system. To a certain extent, this is even true generation by generation, but the neutrinos which show up here, nu e, nu mu, and nu tau, are mixtures of the two particles nu L, nu m, and nu h, so there's some mixture between generations in weak interactions. But more important than that, the charges of all types are rigorously conserved as far as we know. This evidently concerns the electric charge Q that you're familiar with, but also the weak isospin T and T3 and the color charges R, G, and B. The flavor which distinguishes between generations is a special case. It is conserved by the strong and electromagnetic interactions, but can be altered by the weak one. We will define what it exactly means to conserve a quantum number when we discuss Feynman diagrams in part 1.5 first of this module, and then later in video 4.1a. In the next video, Mercedes will introduce in more detail the forces which interact between matter particles.